This is problem 8 of the so-called homework set that I sent out. And what I did was, I guess you've noticed by now that I used 1.5 Henrys for the inductor. And we started off with a very simple R1, and I changed that to 5,000 ohms, and we stuck with that. Our power supply was 1,000 hertz in the last set of problems, and the power supply voltage was 230 volts. So we've had some consistency, so we didn't have to calculate certain items in the circuit over and over again. So here's the circuit. I haven't bothered to put in the frequency or the voltage for the power supply, mainly because we said it was 1,000 hertz, and a 1.5 Henry inductor contributes 9,425 ohms of inductive reactance at that frequency. So everything I've got right here is in ohms, and problem number 8, and I'll just lay it here. I don't know if you can read it or not, but there it is. It is asking us to calculate the real power in the circuit, the apparent power of the circuit, the power factor of the circuit, and the phase angle for this circuit. So let me go ahead and add a few more things that I thought were trivial, but they're not. The power supply is 230 volts. The 1,000 hertz we won't use again, so we will do it as such. Now then, let's see the best way to do it. Let me reveal a secret here, okay? Anytime you have a circuit of passive devices, such as a resistor and an inductor, those are both passive devices, the only item that consumes real power is this resistor. So, just for giggles, let's take a look at this one. Let's say the current in the circuit, which we have already calculated, and I've thrown my paper into the trash, so I'll just continue, is equal to the voltage of the circuit divided by the impedance of the circuit, is equal to 230 volts divided by 10,669 ohms. And let's see, I'm doing this again, but no harm done. 230 volts divided by 10,669 gives us 0.0216 amperes, right? So, the other day, last day in class, we were discussing this, and apparent power that's equal to volts times amperes, or I times V, or I times E, whatever you like to use as designators for that. The apparent power for us is 0.0216 amperes times the applied voltage, 230 volts, and that will give us 4.96 volt amperes. Now that's apparent power. You only have apparent power in AC circuits. You don't have it in DC circuits. So that's our apparent power. I have already told you that the real power is consumed or produced by the resistor. So we'll say for this particular circuit, real power is equal to I squared times R, because that's the power produced by the circuit, and that's equal to 0.0216 squared times 5,000 ohms and I get 2.33. And what are the units? You already know it. Okay, for power it's watts. Okay, so let me pause. Let me find a different color. So apparent power is 4.96 volt amperes. Real power is 2.33 watts. Now then, in all the circuits of the universe, can I say it, or should I say almost all of them? 99.9% of all the circuits in the universe, okay, the real power number will be less than the volt ampere number. Okay, so we have real power. We have our apparent power. And we'll just talk about, we might as well talk about it here. It's not what I wanted to do it, nor is it the way I wanted you to do it, but reactive power will be equal to I squared times the reactance, and for us it's an inductive reactance. So that's going to be 0.0216 squared, and the reactance is 9,425 ohms. And let's see how that comes out. And okay, so this is 4.40, and the units for this are VARs, volt amperes reactive. If you get around the TVA people, you will hear them talk about this. So, there we have it. All right. Now let me check my work here just briefly, if you don't mind. Okay, what I did was I did some verification to make sure all my numbers were correct. And you'll notice that we end up with a relationship which you all will recognize. That says that the volt amperes apparent power, okay, is equal to the square root of the sum of watts squared plus vars squared. And vars is that new strange term, volt amperes reactive. I would like for you to remember that for a little while, but not necessarily long term at this point. So my volt amperes comes out to be 4.96, which is what I had right here, and it is the sum of the square root of the sum of the squares of real power and the square of reactive power. Okay, now that was a good conversation. Is new to you. I would love it if you would commit that to, or a large portion of that to your permanent memory, but there is an easier way. Okay, so let's take a look at this. What we've got is we've got our circuit, right? 230 volts, 1000 hertz. A resistor, a reactor. There's my circuit. I've got 5,000 ohms here. I've got 9,425 ohms here. And we calculated Z. And let me slide some of my windows over so I can read this. Was 10,669 ohms. And let me put this one in here. Okay, we've got that. And this is how I would like for you to remember this. Okay, so we want to know something about power, maybe something about reactive power. We definitely want you to know something about power factor, okay, and the phase angle in the circuit. Now you already know that anytime you have a circuit that has an inductor for its reactor, the current will lag the applied voltage, okay? If it's a pure inductor, no resistance, then the current will lag the voltage by 90 degrees. But here, this is a culmination of everything, okay? Now I'm not going to draw this to scale. So, for this class, we'll have, we're going to have a right triangle. These are two axes. And this one will be X sub L. This one will be resistance. So this axis is 5,000 ohms long. And this vertical axis is 9,425 ohms. Okay, so we'll call them vectors. We'll pretend they're not moving. That's okay. That's about as well as I can do it. Okay, so we have a right triangle here. The horizontal line is resistance, the vertical line is reactance, and then the hypotenuse is impedance. Okay. The definition of power factor in the electrical world is that power factor is equal to the cosine of this angle right here and the cosine of that angle is equal to the resistance divided by the hypotenuse, the impedance, and that's going to be equal to 5,000 divided by 10,669 ohms. Okay, so that is the power factor, 0.469, or you can say, and we electricians love this, 46.9%. Now then, to find the angle, this is the angle by which the current lags the voltage. We have the inverse cosine of 0.469, and for the circuit we're working with here, I get 62 degrees lagging.